Welcome. Today we're going to look at the construction and interpretation of a circle diagram for a three-phase induction motor. As we already know that graphically much information can be obtained, and for three-phase induction motor it's no different. We have this tool called a circle diagram, which we can interpret to give us information regarding this machine. So in order to construct the circle diagram for a three-phase induction motor, two tests have to be conducted on the machine. Firstly, the no-load test, where from your meters, wattmeter, ammeter, voltmeter, you'll be able to record the voltage, current, and power on no load. Thereafter, you do a short circuit test, or rather a locked rotor test, where the rotor would be locked and a very low voltage would be applied, or much lower voltage will be applied to your stator, and again, your current, power, and voltage would be recorded. This is enough information to construct your circle diagram. And from this, we're going to look at how to construct it. So, without further ado, let's get started. Okay, so now that you've conducted the two tests and recorded the various readings, using this formula, you are going to calculate your no load and locked rotor phase angle. So for no load, and if you do that, that would give you about 80 degrees, and you're going to do the same for locked rotor. And that would give you about 75 degrees. Now, there's a slight adjustment that needs to be made. You have to adjust your short circuit, your locked rotor current to the current it would be if normal voltage were applied to your stator. So to do this, you would use a ratio that your new short circuit current to the short circuit current that you read from your voltmeter is equal to your rated voltage divided by your short circuit voltage, or the low voltage applied to your stator. And from this you should get that your short circuit current, if normal voltage were applied, would be 250 amps. Okay, so now we need to construct our circle diagram. For the circle diagram, you are going to extract currents from that, and you need currents. So you're going to use your adjusted short circuit current, and also your no load current is going to be on this diagram. So if a scale is not given to you, you need to look at this value, knowing that on an A4 paper, you can probably use a normal 30 centimeter ruler to construct a line. So how big or how small are you going to make your circuit diagram in order to interpret the data? Of course, you do not want it too small. So in this case, seeing that my largest current is 250 amp, I'm going to use a scale of 1 centimeter is equal to 10 amps. And that would give me, this would be my longest line on my circle diagram. It's the 250 amps divided by 10 to give me 25 centimeters would be my longest line. Let's see how we're going to use this information to start constructing our circle diagram.
Okay, so now I just rewrote all the information down so that I can fit it all into the screen. But now you've got your no load phase angle, and you've got your no load current over here. I'm using a scale. 1 centimeter is equal to 10 amps, and therefore that is going to be 2 centimeters at that angle. Your short circuit phase angle goes with your adjusted short circuit current. So over here I just used the outer perimeter of my graph paper to construct my vertical axis and my horizontal axis, and I said I'm going to try and keep this as simple for you as possible. So the first line you're going to construct is, with this being your 0 point, of course, is your no load current, the 2 centimeter line. And for that, just a reminder, our angle is about 80 degrees. This angle is measured from your vertical axis. So if I'm going to place my protector over there at the origin, I'm just going to measure about 80 degrees over there. What's 79.6? So yes, I haven't got, it's going to be about 80. I'm just going to make a dot to mark that position, because that line from your 0 point is only 2 centimeters. So using from 0 to there as a guide, I'm going to mark out 2 centimeters, only 2 centimeters. So this angle over here is my no load phase angle. You don't have to label that, I'm just doing that to show you. Your other phase angle for your adjusted short circuit phase angle was about, let me just remind you, 75 degrees, 75.06. So again, measuring from your vertical axis, 75 degrees. Now this line is a lot longer, that's 70. Let me just get the right spot over there. And this is 250 amps at a scale of 1 centimeter equals 10 amps. It's going to be 25 centimeters from 0. So, okay, just make sure this fits on over there. Through that point, 25 centimeters over there. Again, this is your short circuit phase angle over there. Now, these are what I refer to as your construction lines. I'm just going to get another color. At this point, firstly, this is your new 0 point. So let me use black for that as well. So from here, let's call it O prime. Okay, you don't, I'm trying to label it afterwards so I don't make it too complicated. Okay, just extend a horizontal line from that point. Let me just make sure that this is straight. Okay, I actually got a nice board, but I wanted to show you can use very simple tools. Just a straight line like that. Okay, from that point. Okay, now we're going to start drawing our circle. I'm just getting another color for that. Again, from that point over there, O prime, to the end of your short circuit current line, you are going to join. It's just a matter of connecting the dots over here until you get to the end. This, again, you don't have to label it, but for the sake of this video, this is your output line. Okay, power over here. So you need to measure this line and bisect it. So exactly halfway you're going to make a mark. So I'm going to have to get in closer here. Try to measure this accurately. So from 0, for me that looks at about 232 millimeters. 232. So about 116 over there would be the halfway mark. Okay, you need to draw. So now you're constructing on your output line a perpendicular bisector. So the line perpendicular to that. There we go. Okay, just a matter of connecting the dots through that point and through that point, however long. Okay, at this point, on this line, which is parallel to your horizontal axis, that point over there, you're going to call C. Now, C, sorry, this keeps going out of focus. C, O prime, is the radius of your circle. Okay, so here I had a little trouble with the sound, which may very well be a blessing. So at this point, you have to construct your circle. Of course, like I said, O prime to C, C for the center of the circle is your radius. And you'll see that that line meets the end of your short circuit current. Just to indicate that that is perpendicular over there. And then again, that is your output line, that is your power. So everything above that line would be the output of your motor at various loads. If I bring your attention right to the end there, that would be your reading at standstill or at starting. So if you construct a line parallel to your vertical axis, straight down to your horizontal axis over there, that line gives you all the information you need at standstill or at starting when your slip is 100%. So in between your new horizontal axis, that is from O prime to the end of that line, and between your short circuit adjusted or short circuit current, that is all your losses in your stator and your rotor, or at least, sorry, that is your stator and the rotor copper losses up to the end over there at standstill. You will notice that there, like I said, anything above your output line is your output at various loads. And as you already know, at standstill, at starting, there's no actual speed, and therefore there is no power out at that point. So for this example, I used equal rotor and stator copper losses. So for equal rotor and stator copper losses at standstill, you'll take the values and you'll divide, or you'll measure that line and you'll divide it by 2. Although, if you are given your your stator phase resistance per phase, you would have to make use of the formula which I am currently writing down over here, that your stator copper losses per phase is equal to 3 I square R per phase. But in this case, for this example, I'm using the fact that the stator copper losses are equal to your rotor copper losses. And for that information, on that vertical line which you've just constructed, you need to measure that line. So from your new horizontal axis all the way to the perimeter of your circle, and you'll bisect that line for equal rotor and stator copper losses. Again, like I said, if you are giving the stator phase resistance per phase, you're going to have to calculate the stator copper losses, and then from your stator copper losses, using that current, you would then measure from your new horizontal axis to whatever length to get the value of your stator copper losses. I am now constructing the line from O prime to that circle, And this line is going to be your torque line. So from O prime to the point which you just made, that is your torque line. Okay, so while I'm busy getting the torque line in here, once you have your torque line, you need to think about this logically. Torque is associated with your rotor. So if there is no actual speed, there would be no torque. The distance from your torque line to the perimeter of your circle gives you the value of the torque or the current. Remember, from the circle diagram, you are taking currents. And here I just want to remind you of the power flow in a three-phase induction motor is that your power into your machine is equal to, I just simplified it here, your stator losses plus your rotor losses plus your constant losses plus your power out. And it would make sense that your power in would be much bigger, or would at least be bigger, not much bigger, but it would be bigger than your power out of your machine. So the distance from your torque line to the perimeter of your circle gives you the torque for any load. So by now you've figured out that the perimeter of your circle, it gives you the various loads. So there are three conditions which you might be asked to obtain information for. So the first one is full load. I'm going to do all three on this circle diagram. So the first one I'm going to construct is your full load line. I'm also going to construct the line for max output and also for maximum torque. Okay, again, the torque is associated with your rotor. Like I said, it might be a blessing that I lost the audio to this video because it seems like I was just rambling a bit over here. I hope I'm not missing out on any vital information. Let's start constructing lines. The first one, as I'm indicating on the page here, is your full load. Your full load, the information you get for full load. So for full load, you're going to draw a tangent from 0 to your semicircle. Over here, remember that line that I'm pointing out is your perpendicular bisector of your output line. So if you draw a line perpendicular to your horizontal axis, which intersects your perpendicular bisector of your output line, you will get the maximum output. And then for the last condition, which is for max torque, I will show you how you will determine that. Okay, so again, full load, maximum output, and max torque. The first line we're going to construct is for full load. And for full load, you are going to draw a tangent to the circle from your origin. So yeah, I'm just trying to get that ruler as close to the perimeter of circle as possible. From my origin, I'm drawing a tangent. This would be for full load conditions. So I've just got to guesstimate about where exactly that line just touches the perimeter of my circle. And again, I'm drawing a line perpendicular to my horizontal axis going through that point. And that would be for full load. So you are going to mark out the point on your base or your horizontal axis, the point over there in your new horizontal axis, the point on your torque line, the point on your output line, and the point on the perimeter of your circle. You can call it whatever you want to. You've already, you see, I like to stick to the letters of the alphabet. C is my center of my circle, so I'm not going to use C again. The following line I'm drawing is the one for maximum output. So remember I said it is where the perpendicular bisector of your output line, and sorry, there you can see that line isn't quite straight. So I'm going to have to go in and go and fix that one, but that would be, if that line was straight, it would be the line for maximum output. The distance from my output line to the perimeter of my circle is the largest at that point. And then now, this is very important. Now for max torque, you're going to take any radius and you're going to make 2 marks on your torque line. Okay, so there where these markings you've made on your torque line intersects with your torque line, you're going to use a larger radius to make again 2 marks from those points, or 2 markings on your graph paper. And there where those 2 markings intersect, I didn't quite get it right the first time, so I just had to go back so I can get a clear point of intersection. From there, perpendicular to your horizontal axis, that would be the conditions for maximum torque. So in other words, I hope this is starting to make sense for you. The distance from your torque line to the perimeter of your circle is greatest there where these lines intersect. Again, you're going to make markings on. Okay, and then here the fact that I didn't draw a straight line for my max output is bothering me, so I'm just going in and fixing that. So I'm very sorry about that. It bothered me, so I'm just fixing that. I'm going to make a marking on the perimeter of your circle and on your output line, on your torque line, and on your horizontal axis, both the new horizontal axis, the diameter of your circle, and also on your original horizontal axis. The distance between your original horizontal axis and the diameter of your circle, that represents your constant losses. The distance between that axis and your torque line, I hope this makes sense to you, are your stator copper losses. Remember, stator out is rotor in. So between your torque line and your output line for any load is your rotor copper losses. And then beyond that, from your output line to the perimeter of your circle is your output. Remember, any value you measure on this circle diagram is a current. So if you have to give a power value, you have to use the formula P is equal to square root 3 V line of whatever current times cos of the phase angle in order to determine the power using your current. In cases where you have to calculate the slip or you have to calculate the efficiency of the machine, because your power will be proportional to the current, it is not necessary to calculate the associated power because it is a ratio. You can just measure the values and use the measurement to calculate values such as efficiency, slip, etc. So how do we take data from the circle diagram? So over here for full load, what I'm currently pointing out is that any line drawn from the origin of your graph to the perimeter of your circle for any load, that is your current at any load. So right now I'm pointing out that OF would be your input current at full load. If you needed to calculate the input current for max output, you would draw a line from your origin to the point of the perimeter of the circle to your output line. And also for max torque, you would do the same. You would draw a line from your origin to the max torque line on the perimeter of your circle, and this would be your input current for those conditions. So right now, again, I'm pointing out for full load because here in this exercise we need to determine the full load input current. So to do that, you are going to measure from O to the point F on my graph, and when I do that, I got about, and also for my power factor, you are going to measure the angle from your vertical axis to that line. And that would be your phase angle at full load. Okay, so once you've measured that line, I measured the tangent to my semicircle, which is my full load line. So from my origin to what I marked to be F now, that would be my input current at full load. I measured that to be about 72 millimeters, and because I use such an easy scale that 1 centimeter is equal to 10 amps, that is actually 72 amps. It won't always work out this way, but in this case it did absolutely wonderfully. And then to get my phase angle for full load, I just measure the angle from my vertical axis to that line, and I got that to be about 29 degrees. And cos of that angle gives me a power factor of 0.875 lagging. Okay, so the next information that I'd like to read from my circle diagram is the efficiency at full load. So again, for the same conditions, the same line that we are currently busy with, we need to calculate the efficiency. Here, I'd like to emphasize that efficiency is a ratio. It compares my output power to my input power, so I do not have to calculate the associated power in this case. I can just measure the two lines and compare them to one another and get the efficiency. So again, your power out is from your output line to the perimeter of your circle, always for any condition, for any load. And your input power would be the entire length of that line which you draw perpendicular to your horizontal axis. Should make sense to you that your input power is bigger than your output. So it's the whole length from what I marked out to be A to F. So power out over power in, that gave me efficiency of about 88% in this case. I did not need to calculate the associated power. So for max output, for max torque, anything, any condition, same thing applies. The next thing is we want to calculate the slip at max torque. So just a reminder, this is the one I remember, that your rotor copper losses is equal to your slip times your rotor in. So therefore your slip is equal to your rotor copper losses divided by your rotor in. So again, it's for maximum torque, so you go to your maximum torque line to get this information. The distance from your torque line to the perimeter of your circle is your rotor input. Remember the flow of energy. Your stator out is your rotor in. And from your torque line to the perimeter of your circle, that is your rotor in. Your rotor copper losses is the distance between your torque line and between your output line. So it is a ratio slip. It compares your actual speed to your synchronous speed. In this case, it's comparing your rotor copper losses to your rotor input. So you don't have to calculate the associated power here. Just measure those two lengths from your torque line to the perimeter of your circle and the distance between your torque line and your output line, and get the ratio there. And when I did that, I got 40 millimeters and 105 millimeters. That gave me a slip of at about 13%. And then after that, I want the maximum output. Now, in this case, they do want you to calculate the power. And remember, the information you get from your circle diagram is current. So you're going to have to take that current which you calculated and then use the formula that your power is equal to the square root 3 times V line, I line, cos of your phase angle, but in this case, the current that you measure in order to get your output. So they want your max output, so you go to your max output line, and remember, between your output line and the perimeter of your circle, that is your output. So you need to measure that line, multiply it by your scale to get the associated current, and then from that you're going to calculate the power. I got the length there to be about 91 millimeters. So in this case, with the scale that I use, it's about 91 amps. And then using that value, I was able to calculate the maximum output power. If there's anything you feel I can do differently, please let me know. If this video was helpful in any way, please let me know as well. And if you'd like me to do more examples, please let me know about that as well. And then I'll see you next time. God bless.